everybody. Thank you all for being here. My name is Delano Ramdas. I'm the technical lead of the platform engineering team at Allen Gray. My job's pretty exciting because a typical day would look like in the morning we'd get in to troubleshoot some systemd service that has failed dramatically because a spot instance in AWS that went off and came back online just kind of blew up the whole system. And then in the afternoon, we're talking about what the correct RESTful term is to name some endpoint. So it's a job that spans the entirety of the stack. But with that complexity comes a lot of difficulty, specifically around testing. And so this talk is born out of a pet peeve that I have with the industry. Whenever there is discourse around DevOps or SRE or platform engineering, the content always centers around what it is academically, why it's a good idea, why you should adopt it, and what are the bare bones that you need in order to start building out an effective platform. But there is scarily little conversation in industry around what happens when you're 3, 5, 10 years down the road of actually having some sort of DevOps team. After you've built out this wild ecosystem of tools and technologies that all of your application devs have come to love, trust, and crucially, rely upon in order to get their jobs done. At this point in the journey, you need to maintain that platform, right? You need to constantly update it, patch it, build out features for all of these highly complex tools. And it's then that some important questions arise. How do you effectively do development work on an existing platform? And importantly, how do you then test that work well without completely breaking the fundamental tools that the rest of your engineering department needs to be up and stable all of the time? So that is what this talk is about. So today I'm going to structure this conversation as follows. First, I'm going to contextualize, right? I want to make sure that we have a common understanding of what platform engineering actually is, what our mandate as platform teams is, and the kind of products that we actually take care of. Thereafter, I'm going to talk about the reality of testing highly integrated in ecosystems. The fact that for most products in the platform space, the testing pyramid is actually inverted. That test and prod is our reality, unfortunately. And then we're going to talk about what we can still do to test safely despite those challenges. Then we're going to look at how we can flip that testing pyramid the right way up, how we can practically apply the techniques of the development world in order to shift testing further left away from the environments themselves. And finally, we'll talk about some less technical strategies to incorporate into the analysis phase of your SDLC, which will then transitively make your testing more qualitative. Along this journey, I'm going to highlight some practical solutions that you can adopt to improve your testing strategies, but perhaps more importantly, because we all like to complain, I'll also highlight some challenges with these solutions, because I think there's often a lot more value in sharing some of the challenges around some approach that has been tried. All right, cool. So let's do this. First, let's contextualize. What is platform engineering? Perhaps let's start first with what a platform actually is. The platform is the chassis of the technology function of a business. It's a mishmash of the tools and technology choices, the processes and the applications with which other development teams are expected to leverage in order to get their jobs done. And those development teams, their jobs likely involved building out the applications that are actually used by your business. Platform engineering teams are the next step in the DevOps teams of old. What then is the mandate of platform engineering teams? The mandate of our teams are twofold. Firstly, it's to take care of the tools and applications that help your developers with their day-to-day development. Think of CI/CD pipelines, Git repositories. Think of tools like Backstage. Second, our mandate is to provide a stable, reliable, highly available ecosystem of runtimes and ancillary services for both your non-production and production environments. Think of runtimes like Kubernetes or virtual machines on EC2 or VMware or GCE or whatever it is. Think of ancillary services like load balancers or proxies, message brokers, secret managers, custom deployment software, and the list goes on, right? Essentially, a platform team's mandate is to ensure that we can provide a sturdy, stable platform which makes developers' lives easier and upon which they can build. So that's what our products are about and what our teams do. So now let's talk about the reality of testing in this space. Most people would be familiar with the testing pyramid, right? You write super specific pass or fail style unit tests at the bottom of that pyramid and to test the bulk of your work, right? You do fewer tests as you make your way up the pyramid because they incorporate broader and more external stuff. Unit tests are cheap and they're safe because it's just code. It's just your little app. But as you go higher up the pyramid, it gets more expensive, and importantly, it gets more dangerous, because now you're testing how your app integrates with its dependencies, how it performs in a fully-fledged environment. There's greater risk that some nuanced part of that integrated environment is going to break. Now this model, it works really well for application development, right? You have your little application that can be tested in isolation, and then you progressively test how it integrates with other stuff in progressively more complex environments. But what if your application was the entire environment itself? That is the reality that platform engineering teams are faced with. The systems that platform engineering teams need to dev and test for are the highly integrated environments that application devs test against in their final end-to-end style of tests. Those end-to-end style of tests, those just make the change and see how it plays out in a real integrated environment, those become the first line of tests, the unit tests, for platform teams. What this may appear to look like then is an inversion of the testing pyramid. Now, the problem with this is that it makes testing safely very, very difficult. We can't just go ham making all sort of experimental changes and testing our assumptions and just seeing what happens, because developers use the environments. To a platform team, even non-production environments are actually viewed the same way as production. It's still super important, and we shouldn't just break it willy-nilly. So we have this paradox where we need to run these just do it and see what happens style of tests on highly integrated systems. But we can't do that because that style of testing will break something. And we can't break stuff because everybody uses all those systems to get their jobs done. So the first thing that I'm going to do in this talk is acknowledge that reality first. See how we can test safely in spite of those difficulties. And then later, I'm going to speak to some of the strategies that we can use to try to flip this testing pyramid the right side up again and actually do the hard yards to get more isolated unit-style tests to happen. Cool. So now let's talk about what we can do to provide the conditions that we need to test effectively in light of that context that I've just explained. And here, we're going to talk about 4 very loose techniques, all of which are related to this idea of segmentation. How we can segment large integrated systems so that we can still run those end-to-end, those just do the change and see what happens style of tests, but safely, without jeopardizing the applications that use those systems and those apps' users. Cool. Number 1. The easiest and perhaps most important thing that you need to do is segment your production environment into a non-prod and prod environments. Make your change on non-prod and test it there. If it's okay, like roll it out to production. Now, this may seem obvious, right? But the segmentation between production and non-production environments that application devs are very used to aren't always implemented with that same kind of segmentation under the hood. Those environments may share virtual machines. They may exist on the same network subnet. Furthermore, many applications in the platform space don't really have or need a non-production equivalent. Take your Git repository, for example, or even Prometheus federators, where by design in certain architectures, they are implemented with a design that spans both production and non-production environments. Nevertheless, this is still a fairly clear segmentation, but it's not good enough, right? Remember, developers still rely on non-prod environments for their everyday jobs, so simply testing infrastructure changes in non-prod environments still jeopardizes an environment that devs use and are actively relied upon. So how can we do better? Assuming that you have distinct non-prod infrastructure, segment non-production itself along some dimension. Apply your change to one portion of non-prod and test it there before rolling it out to the rest of your non-prod environments and then your production environment. Then there's a couple of ways that this segmentation can play out. The most obvious one is you have a strict separation between your non-prod environments themselves, right? Have a dev, int, pre-prod environment, for example. Apply a change to one of those environments, test it there, roll it across the rest of your environments if it's successful. And this segmentation does work especially well for testing services that are already segmented into dev, int, pre-prod, and so forth. However, many applications in the platform space, they're not naturally segmented into those different environments. Say, for example, you have a load balancing system, Nginx, right? You pay for the commercial license, Nginx Plus, and that's billed per instance that you have. You deploy it to some virtual machine. But it should be highly available, so you have 3. Ideally, you'd want one set of instances, so 3 instances, per environment, and if there's 3 non-prod environments, then you can already see how that bloats out the size of your infrastructure, and crucially, in this economy, bloats out the size of your infrastructure cost. So what would be more practical is to have a single set of Nginx instances that takes care of all of your non-prod environments. How then do you segment that properly? When you have systems that operate across all non-prod environments, you can segment out the internals of that system, such that you apply the changes to the segmented portions of that system, you test those portions in isolation, and if that's good, then you can roll it out to your prod environment. Specifically in the Nginx example, we have one set of Nginx instances, but 3 distinct config files, 1 per environment. And those config files can be devved on, tested, and changed in isolation, right? This is essentially just creating virtual abstractions in your system. Now, the other way to segment out the system internals is to segment out the runtime. In the case that we've been talking about, we segment out the system by its servers. One approach would be to use your blue-green style of deployments, where you bring up another server with the change that you want to make on it, you join that to the existing system of servers, and you test that one server. Once you're happy with it, then you can just get rid of one of the existing servers and repeat the same thing. What this does for testing is it allows the impact of any poor changes that you've made, any bug-ridden changes that you've made, to be limited to 1/4 of that system when it has 4 servers in it, right? That could be costly, though, because you're still bloating out the size of your infrastructure cost. You still are bringing up 1 additional server. So another approach would be to use canary deployments. When you make a change, and this is where you make a change to 1 or 2 existing instances, and you run some tests to verify that they work as expected before rolling it out to the rest of your servers. Now, this has been super useful to us in the patching of servers because the impact of security patches, especially at the operating system level, is notoriously difficult to predict. So we test it by applying those patches on 1 or 2 servers, and we do that first, and if everything looks good, then we roll it out to the rest of our servers. But if not, then you only have to roll back 1 or 2 servers that you've applied to the change to. So the problem with this whole strategy of segmenting non-production itself is while you intelligently are limiting impact of bad changes, you can still break something or a part of something, and that part of something could still be actively used by developers. So how can we do better? We can do better by segmenting, by building up an entirely new environment, right? Completely replicate your dev environment, a dev for dev, if you would, Make your change there, test it, and if everything goes well, start introducing it to the live environments that are actively used by your developers. Now, I mention this because most people might think that this is the ideal solution. A completely isolated environment where you aren't in danger of screwing up any running workloads, even in non-production. But in actuality, this doesn't really work very well. I'm going to talk about two problems and a solution to at least one of them. So the reason why it doesn't work very well is because first, like, it's impractical, right? Two reasons. One, it's still expensive because you blow out the size of your infrastructure estate. But two, because it requires you to be able to like recreate infrastructure on a whim from scratch. And to be honest, very few IT shops have all of their automation waxed enough to be able to do that realistically. And that's also the reason why ephemeral environments and continuous integration environments don't work well for platform applications. One of the ways to get around that impracticality, though, is to try to replicate systems locally as far as possible. Now, I know that infrastructure people tend to scoff at the idea of replicating infrastructural components locally because it is actually very hard. But I think that containerization has actually done a lot in this space now. If you're trying to replicate environments like Kubernetes or applications like Kubernetes, you could use something like Minikube. But even for applications that don't typically run on virtual machines, there's no reason why you can't actually containerize that application and run it locally to perform your testing. So take the Nginx example we were talking about earlier. You could still package up all of that config, package up the application that would ordinarily run on a virtual machine, containerize it, and run it locally so that you can perform your tests, even if its eventual runtime is going to be a virtual machine. Cool. The other big problem with this dev for dev segmentation that we're talking about is that, practically speaking, it is essentially just a sandboxed or MVP environment, right? And those environments actually provide very little test integrity. The environment has no real traffic, not even testing traffic from application teams. It probably has reduced resource capacity. It doesn't really have the conditions that we need in order to test thoroughly. It's not the fully-fledged, highly integrated environment that we actually need. We actually tried this, and it failed wonderfully. We built a single node Kubernetes cluster that ran all of the components, worker components, etcd components, and your control plane components. And it was configured exactly the same as our development cluster. But we executed a change on it, and we tested, and it looked good there, so we rolled it out to our real dev cluster. And our dev cluster failed catastrophically, and we actually had to like trash the cluster and build it up from scratch again. What actually went wrong was fairly technical. In our single node cluster, we didn't really need to worry about the kube scheduler intelligently scheduling across different worker nodes, because everything got scheduled to the one node that was this cluster. Whereas in our dev cluster, the kube scheduler had to figure out how to intelligently schedule to the 11 different worker nodes that we had running at the time. It ran into a bug that it couldn't recover from because of the change that we had created or had implemented on it, and so everything like kind of blew up. So using dev for dev environments opens you up to these kinds of problems that you really don't need. Hence, testing on environment replicas aren't actually quite adequate. The final segmentation strategy, and this is going to seem like a cop-out because it is, segment it out of your responsibilities. Make it a vendor's problem. And there's so many vendors popping up in this space nowadays, going cloud native or using a technology partner of some sort. They can provide a bit of your platform as a service, means that you're not completely responsible for the changes that they make and their associated testing risks. However, it does mean that you have to deal with all of the tropes of vendor lock-in and their ridiculous price tag. But more importantly, you lose control and customization of your infrastructure. And nothing feels worse than being completely helpless at the mercy of a vendor, especially when their system goes down for some reason. And then you're stuck there on a call with them, or worse, on a chat with them, whilst their engineers are troubleshooting for hours and you feel completely helpless and you can't do anything. It is not pretty. And at the end of the day, you sometimes just don't have a suitable vendor that can provide what you want at a suitable price point or can provide the kind of niche functionality that you're going to need. So sometimes you're just going to have to build it and run it yourself. So we've explored these 4 broad segmentation strategies, right? And whilst we've done well to run our end-to-end style tests in a relatively safe manner, none of those strategies are good enough. We're still relying quite heavily on those end-to-end tests. We need to shift left, move testing closer to the point of development, more isolated unit-style tests, tests that will happen before that change hits an environment. In other words, how do we flip the testing pyramid the right side up again? The first and most crucial step in this is simple but foundational, and that is that ClickOps has got to go. You have to codify everything. Far too often in DevOps land, you SSH onto a box and you have your 10-step run book by your side that you want to execute, and you just like try to execute it and pray, right? And that's just not scalable. That's not testable, and that's not safe. Codifying your DevOps tasks and your DevOps works turns infrastructure into an artifact like any other, something that can be versioned, something that can be reasoned about, reviewed, and crucially, actually tested. And this is the case for GitOps, right? Tools like Ansible, Terraform, CloudFormation, they're your friends. Practically, though, what are some of the use cases that codification can be applied to? Pretty much anything, right? I'm going to talk about some of them where they've been useful to us. First, automating server provisioning and the installation of an application with all of its config, like the Nginx example that I spoke about earlier, actually packaging it up, packaging up all of that config for Nginx and then having that codified so that you can deploy that through a pipeline or something of that nature. Next, automating the execution of DevOps tasks. Before the days of Fleet, we automated the creation and the update of our Rancher Kubernetes clusters via an Ansible playbook. We've created playbooks to do OS patching for us, like I mentioned earlier. We've got scheduled pipelines in our CI/CD infrastructure to execute cache flushes, storage cleanup, stuff like that, in situations where we really need to, significantly lowering our toil. Codify the scripts that you use to build your machine images. We have a hybrid architecture at work where we've got some machines running in AWS, some running on-prem with VMware. And regardless of where those machines run, they still should all be provisioned the same at startup, right? For that, we codified the scripts that we would ordinarily execute on each machine to provision them at startup, use Packer to generate machine images that could easily be injected into both EC2 and vSphere. Chaos simulation. We recently built out playbooks that simulate disasters, like availability zone failures, complete with a set of verification tests that ensure that our applications can remain, or do remain healthy, to check that they remain healthy, even in that degraded operational state. And the thing is, even when the platform space or the platform applications don't make codification easy, you can do it anyway. The rubber really meets the road when you don't have, or when you have infrastructure that doesn't inherently come with a way to easily codify it. But I'd say that even in the most niche cases, even for applications that seem like they can't be codified, you can still find some way to move the needle towards codification. One great example of where this has worked quite well for us is the case of Grafana. Grafana is notoriously ClickOpsy, right? You build your little dashboard on the UI and you hit the save button. We codified Grafana. We've written our dashboard configuration in Graphinet. We bundled all of that up inside into a container, and we deployed that to Kubernetes. Now, Grafana is stateless, and all changes to Grafana dashboards, they are code changes. Now, the idea of codification is that, oh, I didn't click the thing. There we go. Now, the idea of codification is that if you can reason about code as an artifact, you can battle harden it even before it makes a change to a physical piece of infrastructure. The ClickOps methods of old could not be tested ahead of time. Codified artifacts can be tested. Codification creates the conditions that are needed to actually be able to do testing away from the environment. Now let's talk about what are some of the fundamental type of tests that you could use if you've got your stack codified. And the first thing is code reviews, right? The rigor brought about by code reviews is itself a type of pre-deployment test. But remember, the idea of code reviews aren't just relevant for pull requests or merge requests. Codification makes changes more visible and discoverable for your developers, regardless of when those changes are made. It makes it traceable, it's auditable, we have history, we can see exactly what's been done, anyone can see exactly what's been done and when. That means that you can always interrogate the code, even code from like 2 years ago. Dependent teams can monitor the changes that you're making. They can see exactly when something's changed and don't need to come and bother you for that information. Having this kind of information on hand also means improved test cases because you have more concrete information to play with. Practically, you can furnish your pipelines with analysis tooling that can generate a software bill of materials or explore your Docker images and all of its constituent layers so that your testers are empowered to verify a given artifact, verify its content, its size, its efficiency, and so on. Next, idempotency tests. Now, a lot of tests for runbooks or the first test for a lot of runbooks is, does this thing work now in the current context, given the state of the application right now, given all of the drift that has happened since the last time that this runbook was run? Creating idempotent playbooks means that your code always has to pass that test. It means your code will have to work out of the box against whatever state the target application is in. Syntactic checks, linters, validators, stuff to do basic hygiene checks. In your CI/CD pipeline, run Terraform validate, YAML lint. These ensure that your syntactic or structural failures in your codes or commands are corrected before you try even running them against a live environment. Security tests, run static analysis for secrets or misconfiguration. Third-party security vendors also tend to have APIs that you can integrate into your pipeline. We've got hermetic security checks running against all of our Terraform code in the pipeline to ensure that we never actually release code to production or any of our environments that would eventually fail the security policies that we have in hermetic that monitor the live environments. Leverage dry runs. Dry run everything. Dry runs test if whatever actions you're going to do will actually work without actually making changes to that target application. And it's another way to enforce idempotence, but they allow you to see if you're making any assumptions about what might exist on a server or whether you have access to a CLI or so forth. Terraform has the concept of plans, which is similar. Ansible, kubectl, they all have built-in dry run functionality, and even when you build your own homegrown utilities, build intelligent dry runs for them. Run your dry runs in the pipeline so that with every commit, you test if what you think is going to happen is likely to happen, and you guard against unforeseen mid-playbook execution surprises. Finally, make your build self-testing. That is to say, verify that if what your code does, if it actually does what it says it does, and fail the build of the artifact in your pipeline if it doesn't. Take, for example, building out a Docker image. If in your Docker file you've got an installation of some CLI, test if after the installation of that CLI, if it is actually there. And it sounds trivial, but like you can use like the version command or something like that to test if it actually has installed correctly. And if it's not, the build will actually fail. Your pipeline goes red, and the faulty change that caused that regression, or even the failure to update code to keep up with like deprecations, that doesn't see the light of day. And this is, I think, the closest thing that we can get to unit tests. Now, this kind of stuff becomes a lot easier if you use smart utilities like Ansible, right, which inherently fail if something like this happens. But there is something here about choosing your technology wisely. So this is some of the ways that you can test if you have your stack codified. And I think we've done pretty well so far. We've made significant progress since the test and prod approach that we started off with. So let me ask one more time, how can we do even better? And that is, firstly, to understand what's worth testing. The thing is that infrastructure is broad. The systems that platform teams run can fail at various different places. Knowing what's worth testing becomes your heuristics to saving time and placing emphasis and effort in the stuff that's actually going to yield the most value. But then the question is, how do you know what's worth testing? Now, first, I don't know. But I think you do, and importantly, your teams do. Over the course of time, you will organically learn where your application's pain points are, where the problem areas are, what's most likely to fail, what weird and wonderful niche edge cases your application has. The crucial thing is that when you find this stuff, You document it. When these sort of cases are documented, it's going to make making future changes a hell of a lot easier because you've already got records of what went wrong in the past. Finally, you get better at figuring out what's worth testing by getting better at observability. My current favorite thing is observability-driven development. I think it's super powerful. Monitor everything, right? Build graphs for everything. Get as much telemetry on your systems as you possibly can. You don't know what you're going to need in observability land. You never know what random metric that you just happen to have is going to become uber insightful and helpful. If you have sufficient monitoring, you have incredibly powerful data on hand for testing. Now, observability alone is not testing, but it sure gives you a whole lot of data to inform where you should be testing. It narrows down the broadness of the problem space and provides a clearer picture of what's worth actually paying attention to. Take, for example, performance testing, which is really difficult to get right precisely because it's pretty difficult to define what good performance actually looks like. With the observability approach, you have evidence for what the established baseline for performance actually is. And you can monitor deviations from that baseline that have been instituted by the changes that you have made. All right, so final thoughts. Platform engineering is a tough space. It spans so many layers of the stack. It exposes you to so many weird and wonderful elements of this industry. But it is precisely because of that cognitive load, the sort of cross-cutting system complexity, that quality assurance is ridiculously challenging. But as with everything in technology, you start small. You start with what you have. Bit by bit, day by day, intentional focus creates incremental improvements, which will one day have you looking back and marveling at just how far you've actually come. Thank you for your time.